Okay, good morning, everyone. Welcome back to another session. Before we start, please, do you have any questions for me? Do you have any issues, any comments, any troubles with assignment or something? Okay, so as I always say, whenever you need help, please feel free to reach out, right? Don't wait for it to pile up. Now, talking about piling up, I hope you're all aware that we have our second exam coming up next week, Friday, right? So I've already posted a study guide, so it would be a good idea to start checking it out, right? It's on Canvas files. You'll find it there, Exam 2 study guide. Okay, so with that said, let's just get on to where we left off the last time. Please, I'm sharing my screen. If you can't see, do let me know. 2.6. Okay, so last time the topic we didn't cover was logarithmic differentiation, right? That was on schedule today. So let's look at how we're going to do differentiation by this logarithmic process, the logarithmic differentiation. As I was saying the last time, this is one of the most powerful differentiation techniques you ever learn. And it's very, very powerful in a way that it simplifies the derivatives that you take. It simplifies matters. So let's move on to this. Now, suppose you're asked to differentiate this, right? Now, as I said, on an exam or on a test or in an assignment, they will tell you specifically if they want you to use logarithmic differentiation. But when you are actually doing differentiation on any time, you can apply it if you like, right? So when it applies, you can just use it. Okay, so now let's look at this function, right? We have y equal to s to the 3 over 4 square root of s squared plus 1 all over 3s plus 2 all to the fifth power. Now, for this function, well, if you ask to differentiate this, you can argue that, well, I can just do like the derivative of a quotient, like quotient rule, and then apply product rule at some point, and so on and so forth. Well, that will still work. But it turns out that the expression that you're going to get is going to be very, very complicated. When you do the quotient rule and the product rule stuff, you get a very, very complicated expression. So that's when this thing becomes important, the logarithmic differentiation. So let's see how you're going to use logarithmic differentiation to solve a question like this, right? So this is very, very complicated. It's going to be messy if you use a quotient rule and stuff. As I said, you can still use it. It still works, but logarithmic will be an easier route. So let's get on to the whiteboard and try and solve this question. So this example 6 on the slides. So for this, we have y equal to s to the 3 over 4, and then square root of s squared plus 1, and then all over 3s plus 2, all squared. No, all to the fifth power. All to the fifth. Okay, so now, how do we do the process of logarithmic differentiation? So using logarithmic differentiation, I should probably erase this. I'll probably need the whole space. Okay, using logarithmic differentiation, that's what we're going to do. So the first thing you have to do is take the natural log of both sides, right? So take the natural log of both sides. So take natural log of both sides, right? So you end up doing ln of y equal to ln of s to the 3 over 4, and then square root of s squared plus 1 all over 3x plus 2 all to the fifth power, like so. So that's the first step, right? So take the ln of both sides, right? And then the next step will be simplify both sides using properties of ln, right? So last time I showed you the 3 important properties that you'll be looking at when you encounter the ln. I'll be putting the notes along as I solve them. So simplify both sides using the properties of the natural log, right? So for this one, what you're going to do is first we look at ln of y. So let me just rewrite it. You have ln of y equal to ln of s to the 3 over 4. Then the next one is square root of s squared plus 1 And then the denominator is 3x minus 5 all to the fifth power, if I'm right. Let me check. Oh, past 2 all to the fifth power. Okay, so I missed this. And then 2 to the fifth power. I hope I got the other parts right. Let me see. 3x squared. Okay, yeah, it looks correct. So from this part, recall that when you have ln of, remember that when you have ln of x over y, right? Ln, the log of a quotient is the difference in the logs, right? So you have ln of x minus what? Ln of y. So when you have this expression, you can see that it's a quotient. So right away, you can simplify that as ln of y equal to what? Ln of, so the top function is what? S to the 3 over 4. And then it's a good idea to write this in terms of like a power. So let me just do this, right? So this is the top expression, the numerator expression. So minus ln of the denominator expression. So that'll be 3s plus 2 all to the 5, like so. Right? So now, let's try and see if we can simplify using any of the other properties of logarithm. Well, from here, looking at this place, right? Let's look at these two properties. There are other two additional properties. So this one is the first one. And then the other two are the ln of a product of two expressions. It's just the sum of the ln of the sum of their ln's, right? So that's ln of x, ln of y, like so, right? So when it's a product, just take this, the ln of each of them and sum them, right? And then the last property is ln of some x to a power is equal to, just bring the power in front to multiply the ln of the base, right? So those are the two additional properties you are going to use to simplify at this level. So for the first part, right? The left-hand side is already simplified. ln of y, you can't break it down, right? But for this first piece, the first term on the right-hand side, you see that this one is a product of two expressions here, right? It's s to the power 3 over 4 times what? S squared plus 1 to the power half. So that means with that one, we can break it up using the first property I wrote here for this level. The ln of a product is the sum of their logs, right? So that's just going to be ln of y. And then I have ln of what? S to the 3 over 4. And then plus ln of what? S squared plus 1 all to the half, right? And then finally minus. For this side, let me still rewrite it. I won't simplify it yet, right? So like so. But then you see that these are the bases to a power. This is a base to a power. This is a base to a power. And then we learned that from the property here, the third property, when you have ln of a base to a power, you can just bring the power in front to multiply the ln of the base, right? So that means that for this part, we have ln of y equal to, so for this one, it becomes 3 over 4 ln of x. For this other piece, we have half ln of what? S squared plus 1. And then for the last piece, we have minus 5 ln of what? 3x plus 2. Please, are you okay so far? Any questions? Okay. Now, at this level, we've been able to simplify it to the barest minimum. We can't simplify any further. This is the best we can do. This is the best simplification we can do. So when you get here, you are done. You are done with the simplification. So the last step will be take d over dx of both sides and solve for dy over dx, right? So when we get here, we just do that. So we take d over dx of both sides and then solve for dy over dx. Now I need to do that on the next slide. Please let me know if you need more time here or if you have any other questions here. Okay, so if there are no questions, then let's proceed. So now moving on, I just do d over dx of what? Ln of y. D over ds of ln of y equal to d over dx of what? The whole thing, the whole expression here. So I think the first one is 3 over 4 ln of x, right? And then the next one is it plus half? Yeah, ln of s squared plus 1. So plus half ln of s squared plus 1. And then the next one is it minus 5 ln of 3s plus 2. Okay, so we are here, right? Now, when you get ln of both sides, you just try and get a derivative and solve for dy over dx. So for the first term, you notice that we're doing d over dx of ln of y. So this is like an implicit differentiation, right? Y is some function of x. So if you differentiate this, you differentiate the outer function times the derivative of the inner function. Now the derivative of ln of x is 1 over x, but don't forget we plug in the inner function. So for this left-hand side, you're going to have 1 over y times what? dy over dx, right? Okay, and then equal to, now for this side, we know that there's a sum of functions, a sum and a difference. So we can do it term by term. So for the first piece, let's look at this first term. You see 3 over 4 ln of x, right? So if you apply the derivative, the differentiation operator through, for the first piece, by the constant multiple rule, just ignore the 3 over 4 and then do the derivative of ln of x. What's the derivative of ln of x? That one is standard. It's just, okay, let me just do this. Let me attach this first so that it doesn't become too messy. For the second piece too, this is a constant. So by the constant multiple rule, pull it out and do d over dx of ln of s squared plus 1. And then for this one too, you have minus 5 here. So pull that one out by the constant multiple rule and do d over dx of what? ln of 3x plus 2, right? And then still, I have 1 over y here, and I have dy over dx equal to. Now, as I was saying, for this one, this is standard. The derivative of ln of s is just 1 over x. So you get 3 over 4 times 1 over x. And then for this second piece, you have half here. The derivative of ln of s squared plus 1. You see that this one is a composite function where the outer function is ln. So we can do the simple approach, right? Just differentiate the function, divide by itself. So the derivative of s squared plus 1 is just 2x, divide by itself, s squared plus 1. And then you have minus 5. This one is the same thing, right? So differentiate the function, divide by itself. The derivative of 3x plus 2 is just 3, divide by itself, 3x plus 2. And then when you get here, you can simplify all you want. But then recall that the question is asking for dy over dx, not 1 over y dy over dx. So to achieve dy over dx, you have to multiply both sides by what? Y. So you end up getting dy over dx equal to what? Y times what? We have 3 over 4x. And then for this side, the 2 will cancel out. So we have something like s over s squared plus 1. And then for this last piece, we have just 15 over 3s plus 2. Like so. But we are not done, right? A very important thing to do is recall that we have an explicit solution for y. We have y expressed in terms of x. So unlike the implicit differentiation where we leave our answer, our derivative answer in terms of x and y, you can't do that here, right? Because here you have an explicit solution. So with this part, we just have to plug the y back in so that we get everything in terms of x. So the y is what? Is this expression. So we just plug it back in here. So that means that dy over dx is finally, and then put it in there. I think it's s to the 3 over 4 square root of s squared plus 1. And then 3x plus 2. 3s plus 2 to the power 5. And then all times what? So we have 3 over 4x and then plus x over s squared plus 1. And then minus 15 over 3s plus 2. And that's it. So this will be our final derivative. So that's how you do logarithmic differentiation. And you're going to get a question about logarithmic differentiation on exam 2. Right? Okay, so that's it. Please, any questions here? That's how you do it. So to summarize, the major steps are first take the natural log of both sides and then use the log properties. The 3 properties that you'll be using are the ones I just stated here. Use these properties to simplify to the barest minimum, right? To the barest level. And then after simplifying, you just do d over dx of both sides. And then you'll be applying like, you have an outer function being ln. So you mostly be doing like differentiate the inner function divided by itself. And then sometimes you have a constant attached, so just pull it out by the constant multiple rule. And after you are done with everything, solve for dy over dx. But please don't forget that y has an explicit solution. So you have to plug it back in. You can't leave it in terms of y there. So y is way back there, put it back in there, and then you have the derivative. Please, do you have any questions on this? I hope you understand. Any comments? Any parts you don't understand that you want me to go over? Okay. Anybody needs time here? Okay, then let's proceed. Let me share the PowerPoint. So this is just going to give us notes and explain, right? It's just going to do basically the same thing that I did, but I solved this so that it's not like we are running through the slides, right? I want us to look at each step, right? And then, so yeah, this is just basically doing what we did, right? So you just take the natural log of both sides, use the laws of logarithm to simplify, and then you differentiate. I think this one use a fewer steps, but yeah. And then you get this, but please don't forget to plug back the y in, right? You have an explicit expression for y. So you can put it back in and this will be our final answer. Okay, so this is just summarizing everything on logarithmic differentiation, right? Everything on logarithmic differentiation, the steps that we went through. So just take the natural log of both sides and use the laws of logarithms to simplify, differentiate implicitly with respect to x, and then solve the equation for y prime or dy over dx. Now, as you can see, the logarithmic differentiation, right, is something that can be applied in almost any circumstance. Suppose you have, say, f of s equal to s to the power n, and you say you've forgotten the power rule, right? I know the power is a bit straightforward, but suppose you forgot the power rule, and then you have y equal to s to the power n, and you are like, how do I get this derivative? Okay, well, I can kind of like apply logarithmic differentiation here. See, if I take the ln of y, and then I take ln of s to the power n, then I'm getting ln of y equal to n times ln of x, right? And then using logarithmic differentiation, you see that if you do d over dy, d over dx of ln of y, and then equal to what? D over dx of what? N ln of x. What are you getting? For this side, you get 1 over y dy over dx, right? And then equal to, the n is a constant, so you get n. The derivative of ln of x is just what? 1 over x. It's kind of like weird that someone is going to remember ln of x and not remember the power, but still, yeah, all that the point I'm trying to put across is the rules are connected. It doesn't matter what you use, right? So feel free to explore. You can use whatever rule, as long as you're using it right, you always get your answer, right? So when you get to this part, right, the derivative of ln of s is 1 over x. So you end up with something like, let me continue here. You end up something like 1 over x, 1 over y dy over dx equal to what? N over x. But then, as you can see, we need to solve for dy over dx. So that means dy over dx is equal to what? N over x, and then times what? Times y. But what is y? Put the y back in. Y is s to the power n. So you get this. But then what do you see here? If you have n over s times s to the power n, is the same as what? N s to the power n minus 1. So as you can see, the rules are all connected, right? No matter what you do, whether you're using logarithmic differentiation or anything, you still get back to the same rules that we've established. Okay, please, any questions here? Okay, anybody needs time here? Okay. Now, in general, this is a very important point to put across. Whenever you're dealing with exponents, right, there are 4 cases, right, of exponents and bases. Now, when you're trying to take the derivative, you may encounter something like this. So let's look at an example for the first one, where the b and n are constants, right? The b and n are constants. B and n are constants. That's what this is saying. Kind of like mixed together in there. Okay, so when the b and n are constant, it's as if an example is something like this: d over ds of, say, 2 to the 3. You know, 2 to the 3 is still a constant. A constant to the power constant is still constant. So that's still 0. Right? So that's what this is saying. That when you have a constant base and a constant exponent, the derivative is 0. Now, what if you have number 2, right? That one is a variable base and a constant exponent. An example of that is, say, something like s plus 1 to the square. The base is variable because you see an x there, and then the top is constant. Now, for this, you have to employ the chain rule. So by the chain rule, what do? Differentiate the outer function. This is the outer function, this is the inner, right? That's the inner, and that's the outer. So differentiate the outer function, that'll be 2. Plug in the inner function, right? By the power, we have to subtract 1, and then times the derivative of the inner function, right? So that's the derivative of s plus 1, right? So you end up getting 2s plus 1, and then the derivative of s plus 1 times 1 is just 1, right? So that's an example of the second one. So whenever the base is variable, and then the power is what? It's a constant, then that's what you are supposed to do. Now, the third case is when the base is constant, and then the exponent is variable, right? So an example of that is, say, d over ds of, say, something like b to the 2x. Oh, not b. Let me use a natural constant. Let me erase here. Shift 5. Okay, so let's look at something like, say, 3 to the 2x, right? 3 to the 2x. So for that one, the base is a constant, but the exponent is varying. Now, for that one, you have to use the exponential rule, right? That the derivative of b to the, so note this. like the derivative of b to the x, where b is a constant, so b to the x ln of x, ln of b, sorry, like so. So based on that, this will be a chain rule still, where your outer function is the exponential function, right? And then the inner function is up here. So what do you do? By the chain rule, differentiate the outer function. The derivative of the outer function, we use this to guide us. That'll be 3 to the derivative of 3 to x is what? 3 to the x ln of 3. But we have to plug in the inner function. So we do 3 to the 2x and then ln of 3. Right? And then when we are done with this, we multiply by what? The derivative of the inner, 2x. So that will be equal to what? So that's 3 to the 2x ln of 3. The derivative of the inner is just 2. So that will be your answer. But the actual case that I want you to really pay attention to is when you have the fourth case, the variable base, you have a variable base and a variable exponent. A variable base and a variable exponent, right? So if the base is variable and the exponent too is variable, then you can't use either the third approach or the second or the first one, right? So let me say an example of 4 is d over dx of, say, x to the x. How do you do this? Please, you can't say this is x times x to the x minus 1. No. And you can also say this is x to the x ln of x times the derivative of x. No, it can't work. And you can't even say this is 0 either. Right? So for that case, what do you do? Right? So I'm going to show you how you're going to apply this on the next example so that you can do this, you try this yourself. After the example, after I show you that example, you'll be able to figure this out. Okay, please, you need time here. Okay, so then we come here. So for this one, this question is asking us to differentiate. But then I can see that this one has a base, which is variable, and then the exponent, which is variable. So this one is not like a base, a constant to a power, a constant. So it's not 0. This one is not a base being variable and then the power being a constant. So you can employ the chain rule where the outer function is a power function. No, that can't work. The base is also not a constant. So you can employ like the chain rule where the base is like the exponential function and then do it. No, that won't work either. So what do you do? Well, we just learned about, we just learned about logarithmic differentiation. So we can use logarithmic differentiation here. That would be the first approach. Let me divide this. Okay. Okay, so let's look at the first approach. That one is logarithmic differentiation. So for the variable base, variable exponent, you can use logarithmic. So you have y equal to what? S square root of x. Right. So by logarithmic differentiation, you first take the natural log of both sides. And then use the logarithmic laws to simplify. Right. So the left-hand side is still ln of y. But for the right-hand side, you see ln of a base to a power. So you can bring the power in front. Right. And then ln of the base again. Right. Now, when you get here, what do? You do implicit differentiation. Right. So just attach d over dx of to both sides. So we have d over dx of ln of y equal to d over dx of what? It's a good idea to write this as s to the half, right? So that we know that the power rule is involved. So this is it. Please, any questions so far? Okay, now when you get here, just differentiate, right? The first piece, this one is always going to be the same thing. It's 1 over y dy over dx equal to, for this side, for the right-hand side, you can see that this is a product of two functions, right? So you can employ the product rule. So by the product rule, leave the first one alone, multiply by the derivative of the second function, plus what? Leave the second function, multiply by the derivative of what? The first. So s to the half. And then when you get here, you get dy over dx equal to what? Y times what? The result. So what do you have? You have s to the half here. And then the ln of x, the derivative of ln of x is just 1 over x. Plus you have ln of x here. And the derivative of s to the power half is, by the power rule, bring the power in front, subtract 1. So that'll be half minus 1. Right. But then you have an explicit solution for y. So put it back in. So that means final derivative will be equal to what? S to the what? Square root of x. And then you have s to the half. I won't simplify to the basic form. This the answer, the system will accept this. I will also accept this answer. So let me just do a little brief simplification. Okay, so yeah, this is it, and that's our answer. So now you have the derivative. See, please, are you okay? Anybody has any questions on this solution? Anybody needs time here? Okay, then let's move on to another approach. Well, another approach is you can connect this to the exponential rule, right? So you have y equal to x squared root of x to the square root of x. So I can say, okay, recall that when you have e to the ln of, say, b, then your answer is b. It's kind of like the exponent and then the log of the same base. They will cancel out, and then the answer will be in front here. So for this expression, you can rewrite y to be equal to what? E to the what? Ln of what? X to the square root of x. And you still haven't changed anything, right? But then when you write it in this form, your ln of x to the square root of x is the same as square root of x, ln of x. And now, after getting this, let's get the derivative. So y prime will be d over dx of what? E to the what? Let me write this as s to the half, and then ln of x. So this one is still the chain rule, where your outer function is the exponential function, and your inner function is up here. So by the chain rule, what do? Differentiate the outer function. When you differentiate e to the x, you get the same thing. But then you have to plug in the inner function. So you get e to the what? The inner function, which is this, times the derivative of what? The inner function, which is that. Right? So moving on, you have this equal to this. But e to the s to the half ln of x is the same as what you have here. It's the same as y, right? This piece is the same as y. It's the same as this y. Because y equal to what? Square root of x ln of x. So that means you can put it back in there. You have s square root of x. And then this derivative is a product of functions. So you can employ the product rule. So by the product rule, you leave this one, multiply by the derivative of ln of x, which is 1 over x, plus what? Leave ln of x, multiply by the derivative of the first one. So that's the power rule. So half s to the what? Half minus 1, which is the same answer as you had previously. So those are two approaches when you have the variable base, a variable exponent. So with that said, you can solve for s to the power x. Please, any questions here? So that's all on logarithmic differentiation. Anybody needs time here? Okay. Now let's look at the number e as a limit. The number e as a limit. For this one, let me do this on the whiteboard. Now, previously we learned that e is just a number such that the f prime of the 0 is equal to 1, right? But the question is, what is e itself? Well, if you check your calculator, you notice that e is like 2.71 and so on and so forth. It's kind of like similar to pi. It is non-terminating, right, and non-repeating. So what is the number e, right? Number e as a limit. So let's write e as a limit. Now, recall that if you have f of x equal to ln of x, right, then you know that f prime of x equal to what? 1 over x. And then f prime of 1 equal to 1, right? We know this. Okay, so this is based on the rules that we already know. That's how we're able to obtain this. But suppose I wanted to obtain this from first principles. I suppose I want to find f prime of 1 from first principles. Then that would be limit as h approaches 0 of what? Of f of s plus h. It's been a while since we used this. I hope you've not forgotten. So that'd be 1 plus h minus what? F of 1 all over what? H, right? So if your f of x is ln of x, right, then what will f of 1 plus h be? You just plug in 1 plus h forever you see x. So that'd be limit as h approaches 0, and then ln of 1 plus h minus what? Ln of 1 all over h. But ln of 1 is 0. So that means this simplifies to limit as h approaches 0, and then ln of what? 1 plus h over h. And then we can still simplify further. We get limit as h approaches 0, 1 over h, ln of 1 plus h. But then by the law of exponents, when you have something multiply ln of a base, right, then you can just take that thing to raise to the power. So what I mean by that is you end up getting f prime of 1 equal to limit as h approaches 0. This ln of 1 plus h to the 1 over h. But from the rules, you're able to establish that when you have f of x equal to ln of s and f prime of s equal to 1 over s, then f prime of 1 is just 1 over 1, which is 1. So we can just substitute 1 for f prime of 1 here. So that's limit as h approaches 0 of ln of what? 1 plus h, 1 over h. But then by continuity, when you have limit of a composite function, right? This is a composite function. Your inner function is 1 plus h all to the power 1 over h, right? So if you have a composite function, then you can take the limit of what is inside and then apply the ln on it, right? So for this side, we have 1 equal to what? So that's ln and then limit as h approaches 0 of 1 plus h to the 1 over h. Okay, so now when you get here, don't forget that when you have ln is the same as log base e, right? And you can write it into an equivalent exponential statement. An equivalent exponential statement. So when you have 1 equal to log of something, is the same as what? The base to the power the answer equal to what is in front of it, right? So that means if the base is e here, then it's e to the 1 equal to what? What is in front? So what is in front is limit as h approaches 0 of 1 plus h to the 1 over h. Okay, so this gives us the first expression for e as a limit. So we can say that e is equal to what? Limit as h approaches 0 of 1 plus h to the 1 over h. This is the first property, right? So e is this. So whenever you're evaluating a limit and then you see this, you look at a limit and it's like this, limit as h approaches 0 of 1 plus the h all to the power 1 over h, then that is just e, right? And as I said, this one, when you actually do the numerical, use the numerical approach, you get e to 2.7 something, right? So that's the first thing, right? Okay, now let me move on to talk about some other thing, right? So we just established that e is what? Limit as h approaches 0 of 1 plus h to the 1 over h. Now, what this means is if the general limit is equal to a number, then the one-sided limits are also equal to the same thing, right? So what that implies is what? E is equal to the limit as h approaches 0 from the right. And it's the same as what? It also implies that what? So this implies this, and it implies e equal to what? Limit as h approaches 0 also from the left of 1 plus h to the 1 over h. Right? Okay, so I'm interested in this, even though you can use the second one to also obtain another different limit. I'm interested in this first limit. Okay, so now let's work on that limit. So if you have, working on that limit, you have e equal to limit as h approaches 0 from the right of 1 plus h. I want to get another limit statement for e, right? So let's say, let x equal to 1 over h. Now, I'm trying to rewrite the limit from h to x, right? So if x is equal to 1 over h, then as h approaches 0 from the right, can anyone tell me what this x will approach? As h approaches 0 from the right, what will x approach? I hope you still remember these things from chapter 2. Can anyone tell me what that is? As h approaches 0 from the right, what will x approach? Okay, so I see something in the chat. Perfect, Brian, thank you. It's infinity. That is true, right? It is 1 over 0 from the right. So like 1 over 0.00001, and that's infinity, right? So that means that you can write e to be equal to, now let's take the limit from h to x. So when the h is approaching 0 from the right, we can replace that with x approaches what? Infinity, right? And then we have 1 plus h, but we are changing everything from h to x. So when the x is equal to 1 over h, then what is h? Right? When x is equal to 1 over h is equal to what? 1 over x. So that means where we have h, we can just put 1 over x there. And then what is 1 over h? It's just x. So we get another second important equivalent limit statement like this. Right? So when you see this, then you know it's e. When you see limit as x approaches infinity of 1 plus 1 over x to the x, it's e. Right? And when you also see limit as h approaches 0 of 1 plus h to the power 1 over h, that's also e. So this will come up in chapter 3.8, right? So we are establishing them here. Please, any questions here? I'm not going to ask you to prove any of this, but when we get to the 3.8, where I'll use this, I don't want it to appear as if I just conjure the e being some limits from somewhere out of thin air, right? So everything has to make sense and add up. That's why we've established this here. Please, do you have any questions on the approach? Is there any part you don't understand for this derivation? Okay. Anybody needs time here? Okay, so this derivation is going to be the end for this chapter, but let's walk through the PowerPoint slide, right? And then wrap it up. So it's just going over what I did, right? So based on the rules, we know f of s, ln of s, this is 1 over s, f prime of 1 is 1. You use the limit definition, you're going to get this, right? Okay, and then as I told you, when you use the numerical method, you can get this value to be e. And then you can also get an equivalent statement when you make this substitution. And you consider where this is, it used the h for x in this case, yeah, but it's still the same idea, right? So we are going to get e equal to limit as n approaches infinity of 1 over 1 plus 1 over n all to the n. And that's all for this section. Okay, so now let's move on to 3.8. So for 3.8, we are just going to, now we are done with the limit laws. We've learned all the limit laws. So here is more about application, right? So for this 3.8, you are going to learn about exponential growth and decay. Exponential growth and decay. Okay, so in many natural phenomena, right, quantities grow proportional to their size, right? So suppose you leave like a population of say 10 people, you mix them up, they say male, female on an island A, and then you make say another population, male and female, of 100, right? The first one was 10, and then the next one was 100. You also put them on another island, say B, and then you assume that they are going to get their food, everything. Like there won't be like a disease, an outbreak of a disease which might kill an entire population on one of the islands or any other thing. So all other things being equal, right? All other things being equal, you expect that the island with 100 people will, at some point, after some years, like say, I don't know, 20 years, when you go to the island with what? With 100 people, which you put on initially, right? You put on 100 people initially. And then the one versus the one with 10 people, which you put on initially. You expect that the 100 people will have a greater population than what? The one with the 10 people, right? So that's what this is about, that many natural phenomena, some things, their rate of change, right, is proportional to their size, right? Like, for instance, population, like I just taught you, right? So for this one, what you are trying to say is, if you have a function y equal to f of t, right, it's a number of individuals in a population of animals or bacteria at time t, then it's reasonable, like what I just demonstrated, like to expect that the rate of growth is proportional to the population, right? The rate of growth. So that means for this one, you have something like the rate of growth, which is the derivative. So that's f prime of t equal to k times what? F of t. So that means the rate is what? Is proportional to what? The function itself, right? So this one is saying under ideal conditions, right? Unlimited environment, adequate nutrition, immunity to disease. This model is going to be very, very accurate, right? Okay. So now, in physics, so these are just examples. So in nuclear physics, you have also the mass of radioactive substance also decaying at a rate proportional to its mass, right? And then in chemistry, the rate of a unimolecular first order reaction is proportional to the concentration of the substance. I think it will make very much more sense if you are working in that field or if you've encountered these problems, right? But they all make sense. Well, the money part is everyone knows, right? Suppose an investment is earning, say, 5%. If someone puts in 100,000, the person expects to earn more than some other person who puts in, say, 10,000, right? So it's still proportional to the size. So for each of these cases, you see this thing play out, right? So we notice that if you have y of t to be the quantity we are talking about, then the derivative, the rate of change, is just proportional to the function itself, right? So you have this equation, dy over dt equal to what? Ky, right? Where k is a constant. Okay, now this model that you see here is called the law of natural growth, right? If the k is positive. If the k is positive, then that means it's increasing. The quantity is increasing, right? So if the k is positive, it's called the law of natural growth. Now, on the other hand, if the k is negative, then it's called the law of what? It's called a law of natural decay. Now, this equation also that you see here, you see that it involves the derivative and then the function itself. So whenever you see an equation which involves a derivative and a function itself, it's something we call a differential equation. When you get to Math 182, you start solving this. I think it's in chapter 11 or 11 something or 9 point something. Yeah, but you start solving some of these differential equations. So just know the name at this point, right? Okay, so that's all. That's this, like definitions and definitions. Please, do you have any questions on the definition? Any issues? Okay. So now let's try and see. The question is, looking at this equation, right? This equation is this. So we have dy over dt equal to ky. The derivative of the function is proportional to the function itself. And my question is, do you remember among all the differentiation rules we did, do you remember which function's derivative is proportional to the function itself? Which function is proportional? The derivative is proportional to the function itself. Which function is that? Is it a power function? No. Is it which one? Okay, let me see. Thank you. It's the exponential function. The exponential function is proportional to this to itself. So that's where we get the solution for this differential equation is. As I said, you go much more into details about solutions of differential equations in your later math classes, if you should take further math classes. But for now, we can clearly see that a function whose derivative is the constant multiple of itself is just the exponential function. I think I got here and then quickly went back. I wanted to talk about that before. So that means if you want a solution to this, the function has to be what? The original function y of t is supposed to be what? Something related to the exponential function. So this is the structure. So you just see e to the kt, right? So how come this is the structure? Well, let's look at this. If we differentiate this, let's see if it's proportional to the function itself. So if you try and get y prime of t, right? So you have y prime of t. This one didn't do much more justice. Let me do this. So just see e to the kt, right? The k and the c are constants, right? So for this one, you do constant multiple rule, pull out the c, you d over the t of what? E to the kt. And then for this side, you do what? The chain rule, because this is an inner function here, and then an outer function, right? So by the chain rule, you have differentiate the outer function, e to the derivative of e to the t is e to the t, but we have to plug in the inner function. So that means you get c e to the kt times what? The derivative of the inner function. What's the derivative of kt with respect to t? It's just k, right? So that's how come we get what? K c e to the kt. But c e to the kt is still the yt. That's why we get k y of t. So this establishes that this is a solution to the differential equation, right? So it's a solution because similar to what you had for quadratic equations. If we say 1 is a solution to x minus 1 equal to 0, what it means is if you plug the 1 in there, you get the equation to hold. So in the same sense, if you plug this c e to the kt into that differential equation, the condition is satisfied, right? So that's why it's a solution. So now moving on, it turns out that if you have an initial condition for this y of t, say we plug in 0, right? We plug in 0 of this y of t. Don't forget that the y of t is c e to the kt. If you plug in 0 for t, then you're getting just the c. So that means that the constant c is just the initial value of the y, right? The constant c is just y of 0. Now, all the things I've been saying and blah, blah, everything boils down to this point, right? This equation. I'm just talking about how we obtain it, but this is what you need, right? this one, and then this property. So everything boils down to this. So that means that for this model that we are considering, the y of t is always going to equal to what? The y of 0 and then e to the kt. Now, let me give you a summary of the whole chapter. This entire chapter is based on this model. This is the same model we'll be using all along. But then we will consider population growth. Under population growth, the y will change to p. And then the k is positive. That's all. The y will change to p, the k is positive. The same equation, the same rules. The radioactive decay, we will just add something we call half-life. And then the k will be negative. And then the y will change to n, standing for mass. That's all. And the interest rate, the y will change to a, which will represent an amount, right? An amount of money. And then the k will be something we call an interest rate, right? So it's the same formula. So it's very simple. It's this the same formula, but we have to identify these things based on the question that we have, right? So that's technically the end of the chapter, but it's the same thing. That's the summary, right? So let's walk through the problems one at a time. Okay, so now we go to population growth. So for population growth, right, we are considering what population P at time T, right? The size of population at time T. And as I told you, it's the same thing, right? The Y has just been replaced with P, right? The rate of change of the population is proportional to the population at that time. Now, this K has a name under population growth. It's called relative growth rate. So that means that in a population growth question, right, in this model, when you hear blah, 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 blah has a relative growth rate, then you know that that's your K. Or solve for the relative growth rate, then you know you are asked to find the K, right? Okay. So instead of saying the growth rate is proportional to population size, we could say the relative growth rate is constant, right? Okay. And then because we know K is a constant. Okay. And then appears in the coefficient. Okay, yeah. So we know that. So for instance, if you are given the model like so, you know that this is your K, right? This is your K. And that's your relative growth rate. So you can say that the relative rate of what? The population growth at a relative growth of 2% per year. So if you're asked to interpret this, then just pick the K from here. Now, if you know your K to be this, then that means your model simplifies to this, right? It's P of T equal to what? P of 0 e to the what? KT. K is 0.02 here. So as I told you, all the models will follow Y of T equal to what? Y of 0 e to the KT. But the variable Y will change based on the problem context. So it's a population. So it's just P, same model. Okay. Please, any questions so far? We'll be working on examples soon. Anybody needs time here? Okay. So let's look at the first example. So use the fact that, example 1, use the fact that the world population was 2560 million in 1950 and 3040 million in 1960 to model the population of the world in the second half of the 20th century. Assume that the population, assume that the growth rate is proportional to the population size. So that's a cue that we are going to use the model that we just talked about, right? The growth rate is proportional to the population size. Okay, what is the relative growth rate? That means it's asking us to find the K. Use the model to estimate the world population in 1993 and to predict the population in the year 2020. Okay, so then let's do this. I'm going to do this on a whiteboard. This 3.8. Example 1. Okay, so it says it's 25.6 million in 1950. So 1950, we have 2560 million. And then in 1960, we have 3040 million. And then it says use it to model. Okay, so great rate of constants, use the model. Okay. So I have everything now. Then when I'm done with this, I'll just move on and solve the other pieces. Okay, so if you're going to use this to model, the first thing we have to identify is what is the model we are going to use? Well, the model is P of T equal to P of 0 e to the KT. That's the model. That's what we have to know. Okay, now let's try and look at what we are given here and try and solve for the parameters. right? It's 11:49. Okay, let me try and at least get a K, and then we'll continue with this example the next time we meet on Friday. So since you are modeling and the least year we're given is 1950, I will equate the time zero to be what? The year 1950. Now, if the 1950 equates to the time being zero, then that means that 1960 will equate to the time being 10. So what this means is in 1950, that's P of 0, right? Then I have P of 0, e to the what? K 0. The population is what? P of the 0 is what? 2560. So essentially that's P of 0. So I have one parameter solved for. Now this is in terms of millions, right? It's in terms of millions. Is it time? Okay, yeah. It's in terms of millions, right? So without further, let me just write this one. We continue on Friday. So that means I have 2560 e to the kt. Now, next time on Friday, I'm just going to continue with to find a k, right? Come on, 60 e to the kt. So this million. So next time on Friday, I'll just continue from here. Yeah, solve for k, and then we will wrap up the other examples. So thank you for your time. Enjoy the rest of your day. See you on Friday.
Thank you.
You're welcome.
Thank you.
You're welcome.